So here we go. Last big day of graphing in Chapter 3. We're in Section 3.6, and the goal of this chapter, or of this section, is to put it all together. So we're trying to create these graphs now. So what's going to happen? Including all pertinent information. So what's that going to mean? That's going to mean extrema. That's going to mean inflection points and intervals of concavity, and that's also going to mean asymptotes. So we got a lot of stuff going on here. So your equation x squared minus 2x plus 4 over an x minus 2, we got a lot of crazy stuff. We're going to put it down here. I'm going to zoom this in so I've got lots and lots of room to work as we're going through things. So we're going to start off extrema, inflection points, asymptotes. Let's start with what I would suggest is the most important thing. Let's start with asymptotes. So asymptotes, let's start with vertical ones. Well, let's see. That numerator is not going to factor, and the denominator cannot be x equals 2. So we know we've got a vertical asymptote at x equals 2. Definitely. No problem. So that part's taken care of. Now, what about non-vertical asymptotes? So non-vertical asymptotes. Well, remember the key to taking non-vertical asymptotes is we're going to do the limit as x approaches infinity. So limit as x approaches infinity, x squared minus 2x plus 4 over an x minus 2. We're going to multiply top and bottom here by, it looks like, a 1 over x. We don't have a square root or an absolute value, so we don't have to worry about those. So if we do that, how about limit as x approaches infinity of, pardon me, let's see, how about x minus 2 plus 4 over x over a 1 minus 2 over x. And if we look at this and we carry out this limit, we're going to end up with that limit ended up being infinity on the top and 1 on the bottom with our direct substitution. So what does that mean? Well, if you think back to your days in pre-calculus, if we take an x squared equation generically and we divide it by an x to the first equation generically, we're going to end up with a result that is an x. That x would mean a diagonal line. What we actually have in this particular problem is we actually have an oblique asymptote. And the way that we find an oblique asymptote, this one's going to turn out to be an oblique asymptote. How do you find your oblique asymptote? You do the division. So let's do synthetic division. We're dividing by x minus 2. So let's put a 2 out here, synthetic division, a 1x squared minus 2x plus a 4. If we do the synthetic division, here's a 1, 2, 0, 2 times 0 is 0, 4. That 4 is my remainder. I throw out my remainder. What do I have left? This is y equals x plus 0. That y equals x plus 0 is your equation of your oblique asymptote. So what have we found so far? We found 2 asymptotes. Our experience here with with an oblique asymptote, let's go down the graph and let's put them on that graph. So if we work our way down here to this graph that we created, so we found a vertical asymptote at x equals 2, an oblique asymptote at y equals x. So y equals x will be a diagonal line working through here somewhat. So we know about behavior around asymptotes. So we know it's going to have to try to get close to that blue line and that pink line, and we'll just have to figure out how. So working our way back up, we found those things. Intercepts. How do you find intercepts? Well, let's see. What we could probably do, let's hold off on intercepts. We'll find those in a little bit. Let's take care of extrema next. So if we talk about extrema, we're going to need a derivative. So I go to take my derivative, my f prime of x. Quotient rule, bottom. Derivative of top. Pardon me. 2x minus 2 minus top. X squared minus 2x plus 4 multiplied by the derivative of the bottom. Don't forget to square that bottom and do not multiply it out. So if we do that, let's see. Simplifying 2x squared minus 4x minus 2x minus 6x plus 4 minus x squared plus 2x minus 4 over the top of that x minus 2 quantity squared. Clean it up. It looks like we have an x squared minus 6x plus 2x is minus 4x. And it looks like those 4's cancel each other out over my x minus 2 quantity squared. What I think I'm going to do then is I'm going to go one step further here and say x quantity x minus 4 over an x minus 2 quantity squared. And so now let's see. So if we look at critical numbers, so critical numbers on the top, x equals 0 and 4, and those would be smooth parts of the curve. denominator x equals 2, and don't forget that x equals 2, we found at the beginning of the problem was a vertical asymptote, so we'll make a little note about that. Pardon me, intervals. So if I make my intervals right now, so my intervals, let's see, we're testing f prime, so it can tell us about f. We're going to take these things interval, negative infinity to 0, 0 to 2. Even though 2 is going to be a vertical asymptote, we still have to test it because the equation, the behavior might be changing around it. 2 to 4, 4 to infinity. Let's see, so if we take that derivative, we plug in a number like negative 1. Let's see, we'll get a negative times a negative on the top, and we'll get a positive no matter what we put in the bottom. So here's a plus. That means my function is going to be increasing in that interval. If we go to plug in a number like 1, positive on the positive x, negative in the x minus 4, that's going to be a minus. Function's decreasing. Looks like I just found a relative maximum at the point 0. We'll figure out where in a second. Let's see, so plug in a number between 2 and 4 like 3, positive, negative on the top, positive on the bottom. Looks like we're going to end up with a negative, which means my function is still decreasing, but it doesn't matter because remember at the beginning of this problem we found out that this was a vertical asymptote, so it couldn't be a max nor a min. And lastly, we'll plug in a number like 5, positive on the top, positive on the bottom. Positive, which means my function is increasing, and therefore we just found a relative minimum at the point 4 something. Now, what are the somethings? How do I get those values? Remember, you go back up to your original function. So original function, if we plug 0 in, the numerator looks like we're going to have a 4 on the top and a 2 on the bottom. So that's 0, negative 2. Plug in 4. 4 squared is 16, minus 8 is 8, plus 4 is 12, divided by 4 minus 2, divided by a 4, or divided by a 2. I think this is the 0.46. So again, taking that information, we know relative max at 0, negative 2, relative min at 4, 6. Let's come down to our graph. Let's put those on there. So 0, negative 2, and 4, 6. And it makes sense because it looks like the point 0, negative 2 is supposed to be a relative maximum, and the 0.46 is supposed to be a relative minimum. Both of those numbers make sense. Now let's support them. Let's figure out what's going on with concavity and all that kind of fun stuff. So concavity, we're going to need to take the second derivative. So my second derivative, let's see. I think I'm going to go ahead and use this form of the derivative when I go to do it. So my second derivative, let's see, bottom x minus 2 quantity squared times the derivative of the top, which would be a 2x minus 4, minus the top, x squared minus 4x, multiplied by the derivative of the bottom, which is going to be a 2 quantity x minus 2 to the first times a 1. All of that is being divided by an x minus 2 quantity to the fourth. Yuck, that is a nasty derivative. But you know what I'm looking at? In this numerator, I see two terms. I see a term here, and I see a term here. What do they have in common that we could make life a little bit easier on ourselves? Well, I see that they both have an x minus 2 in them. So how about if we factor out an x minus 2 from each of those terms? And if I do that, let's see, what will I have? This first term, I'll have an x minus 2 times a 2x minus 4. And in this second term, I will have a 2 times an x squared minus a 4x. So what I did is I actually made my algebra a little bit easier by taking those out. And when you look at this denominator in comparison, x minus 2 quantity to the fourth, we can do a little canceling. Why don't we take this this x minus 2 here and this x minus 2 to the fourth and make it to the third? That makes things a little bit easier. And now I still have nasty algebra, but it's not as bad as it was before. So let's clean this up. So how about 2x squared minus 4x is minus 8x plus 8 minus 2x squared plus 8x, and over the top of an x minus 2 quantity cubed. Okay, well, what's going to happen? Looks like the 2x's are going to drop out. Looks like the 8x's are going to drop out. Nice. After all of that, we end up with an 8 over the top of an x minus 2 quantity cubed. And what do we know about that? Well, there are no, so the only critical numbers, there's none from the top. And the bottom, it's only x equals 2, which we already know is a vertical asymptote. So if we're checking for our intervals of concavity and therefore our inflection points, we can tell right now that there's no inflection points to this thing because x equals 2 is a vertical asymptote. So intervals, negative infinity to 2, to infinity. We're plugging into the second derivative to tell us about what's going on with our original function. Well, the numerator is always positive, so if I plug in a number like 0 in the bottom, I'm going to end up with a negative number, and therefore this function is going to be concave down. And if I plug in a number like 3 into that second derivative, I'm going to get a positive on the top and a positive on the bottom, which means this function is going to be concave upward. And there's no inflection points because, again, we have a vertical asymptote at x equals 2. Therefore, it's a place where concavity does change, but it's not a point, so therefore it's not really an inflection point. What do we know about this thing? Well, we've got an asymptote. It's got to be concave down around this point, so that means it must be going to get close here, going to get close here, concave down, relative maximum. There's part of my graph. Other part of my graph, concave up with a minimum at the point 46, so it's going to get close here. It's going to get close here. I look at my graph. All those asymptotes, all those other crazy things. The only thing we didn't talk about is we didn't talk about what happens with the intercepts. How does a person find intercepts? How about a quick review of how to find intercepts? Well, one thing that you could conclude right now is that we don't have an x-intercept because of that graph. And our y-intercept, remember, if I want to find a y-intercept, we're going to do f of 0, which we already found was negative 2, which makes sense. We already found the y-intercept. But if I want to find an x-intercept, remember you're going to set, the fast way to do it is to set the numerator of this function equal to 0, which was x squared minus 2x, let me make sure I got the right function, x squared minus 2x plus 4, set it equal to 0. Well, we can already tell there's not going to be any, but what would that look like algebraically? Well, if I tried to factor it, it won't work. If I try to do quadratic formula, my x would be, let's see, 2 plus or minus the square root of b squared, which would be 4, minus 4 times a times c. And as soon as I'm done writing that down, it doesn't matter the 2 times 1 on the bottom because this quantity right here is 4 minus 16 inside that square root, and that would be imaginary. Can't take the square root of a negative number, so therefore there is no x-intercept. So there we supported it algebraically. We had already kind of figured that out graphically, again, one way or the other. That also asked to find intercepts on this problem. And we've got this really, really cool looking graph.